Okay. Let's begin. Any questions from what we did last time? Anything that was fuzzy before we move on? If not, let's move on to talk about domains. So we're still in 1.1. There's a lot of ground we have to cover to make sure that we're on the same page and we start getting into really serious things. So we're going to continue with 1.1 and we're going to talk more about domains of functions. What's the domain of a function?
All possible x values.
All possible x values are input values,
Yeah.
more specifically. Okay. All right. So now we're going to talk about alt. Right. This is basically the set of possible input values. Another thing, it may be a necessity or imposed restriction. So basically what we're defined for. So for example, let's go polynomials. Right? So we remember what a polynomial is. What do they look like? Well, this is a function that has a certain form, right? It looks like an x to the n plus an minus 1 x to the n minus 1 plus da da da, all the way down to these where our an's are constants. N is a non-negative integer. Right, so examples of those guys are like y equals x squared plus 2x plus 1, or y equals 1 minus 3x cubed, or y equals 4x to the 5th plus 2x squared minus 3x plus 2. Right? These are polynomials. Now for polynomials, the domain of a polynomial is what? What possible x values can I plug in here? All real numbers. Right? Pretty much any x value on the number line I can plug in here, and this will give me something that works. In other notation, which is often what we're going to use, let's call it interval notation. How do you write this in interval notation? Right? Basically to say anything on the number line. Yeah?
Negative infinity to positive infinity.
Right. There's an open parenthesis, negative infinity to positive infinity. So that would be the domain of a polynomial, as long as I didn't impose a restriction on it. I could actually artificially impose a restriction, and then that would be the domain. Right? So, example. Find the domain of x, and I can say here f of x is 3x to the 4th minus 2x plus 1, and then for b I can say f of x equals 3x to the 4th minus 2x plus 1, however, let x over 2 minus 1 and 3, for some reason that has to do with the context in which I set this equation up. Now in this case, the domain of f is all real numbers. There is no restriction. While in this case, the domain of f is just going to be numbers between minus 1 and 3. Right? So sometimes I can impose a restriction for some reason. Right? So it depends on what my function is representing. But in general, for a polynomial, anything can work. but they might impose a restriction on you artificially. So polynomials are nice. They kind of work everywhere. They're very nice functions. They're continuous. Their domain is everything. Other kinds of functions. So let's look at things like radicals. Let's look at something like the domain of the nth root of x, right? Radical x. What is the domain here?
Like, whatever.
Right, so for example,
No,
I can have the square root of x, I can have the cube root of x, I can have the fifth root of x, etc. Right? Things of that form. What is the domain?
0 to infinity. No. It can't be negative.
What's the domain? Possible x values. What are the possible numbers I can take a square root of? Possible real numbers.
1.
Sure. But like all of them.
1 to infinity.
No. I can take the square root of a half,
Um,
and a quarter, and an eighth.
Any number but 0.
yeah.
0 actually works. I can take the square root of 0.
So 0 to infinity.
0 to infinity. Okay, what about the cube root?
Like your
Nope.
rational numbers.
Nope.
Negative.
Do you understand what this means?
Square root.
The nth root of something. What does it mean?
It means the same number multiplied n amount of times gives you whatever number underneath the radical.
Right, the nth root of x, basically, this is the number that gives x when raised to the nth power. Right, so it's kind of like doing the inverse operation of raising to a power. So for example, and of course, if the power is a 2, you usually don't write it, right? So that's called a square root. So for example, I can say the square root of 4 is 2, right? Because if I take 2 to the 2, since 2 squared is 4. Or I could say the cube root of 8 is also 2, since 2 raised to that number will give me 8, right? Can I take the cube root of minus 8?
No.
No.
Turns out I can. It's minus 2. If I take minus 2 and I cube that, I actually get minus 8. Could I take the square root of minus 4?
No.
This one, not a real number. Right? There's no number that I can multiply by itself and get a negative. Could I take what about the fourth root of minus 4?
No.
No, because once I raise something to an even power, I'm always going to get a positive, right? Once I raise any real number to an even power. So there's no, so if this number here is even, it stands to reason that the guy under here cannot be negative, because it just won't make sense. Okay, so now, with that in mind, what if I ask you, what is the domain of this guy? What would you tell me? Well, it depends, right? If your n is odd, it will give you a different answer from if your n is even. Because when you're raising to an even power, you kill negatives. If you're raising to an odd power, you don't. So what's the domain of such a function? If your n is odd, what would the domain be? Anything, right? I can plug in negatives, I can plug in positives, I can plug in zeros. The domain will literally be all real numbers if my n is odd. If my n is even, it's only things that are 0 or bigger. Yes?
So you can only put a negative number under square root when it's an odd.
when it's an odd radical, right? Because odd powers can achieve negatives. Even powers can't. Okay? So that's a very important thing to know, radicals. Here's another thing to talk about, rational functions. So for example, what is the domain of 1 over x, for example?
Anything but 0.
Anything but 0, right? So this is the set of all real numbers, because we can't divide by 0, remember that's a philosophy, except 0. How do I write that in interval notation? Sure, 0 to infinity can work, but what about the other guys?
Negative infinity to 0.
Negative infinity to 0, and what do we do to connect them? Union, right? Which means or. I can be over here or I can be over here, but I can't touch 0. So that's why I have an open parenthesis. I was going to tell you about logs and exponentials, but maybe I should talk about what those are before I tell you this. In general, here, polynomials is all real numbers. For radicals, all real numbers if odd radical, and otherwise where otherwise if n is even. What is under the radical must be greater than or equal to 0. We also have for rational functions the domain is all numbers such that the denominator is non-zero because we cannot divide by 0. Note, these restrictions may be mixed. So I can have a function that combines several of these and I have to worry about all of them at once. And there are other functions we'll talk about when I introduce them, like exponentials and logarithms. We're going to cover that in sections 1.5 and 1.6, and I'll talk about the domains of those when we get to them. Okay, so for now, let's do some examples. Let's find some domains. Find the domains of the following. F of x equals 2x squared plus 5. B. G of x equals 3 over x plus 2. C. H of x equals x over x squared minus 9. D. J of x equals radical x. Which at this point is kind of silly, let me put radical x over x squared minus 9. E. R of x is equal to 4 over the radical of x plus 3. Okay, let's start with A. What's the domain of F? Everything, a polynomial. That was easy. B. What's the domain of G?
All numbers with negative 2.
All numbers such that, what do we not want? Well, it's a fraction. We know we can't divide by 0, so we want the denominator to not be 0. Such that x plus 2 is non-zero, which means that your x cannot be minus 2, right? Because we set that equal to 0, you get x equals minus 2. Now, how do I write that down? As an interval.
Negative infinity, comma, negative 2, and then close parentheses, big U, and open parentheses, negative 2 to infinity. Close.
So that would be the domain for that one. That covers everything but negative 2 is not included. C. It's domain.
Same thing, the same exact thing, except everywhere you see negative 2, put 3.
For C. Well, what do we want? We want all numbers such that x squared minus 9 is non-zero, right? So how do I make sure that's non-zero? What are my possible solutions? How do you solve for x? What's x? You could do that. You can add 9 to both sides, take the square root of both sides, and that would give you a plus or minus 3, right? Or you can realize that you can actually factor that. That's x minus 3 times x plus 3. That's a difference of squares. Right? And so you get your x equals 3 or your x equals minus 3. So there are two bad numbers here. So now how do I write down that domain?
Is it negative
This
infinity?
means if you're drawing a picture, which sometimes often helps, let's actually do that first and then you can give me the answer. So minus 3 and 3 are the guys that I have to avoid, right? So these are open circles. Where can we work? Well, pretty much anywhere else, right? So I can be anywhere over here, I can be anywhere in between, I can be anywhere over here. So in other words, my domain of H would be infinity 2.
Is it negative 3 to 3?
Minus 3 to 3.
Okay. 3.
And it will be union 3 to infinity. D. Draw this one.
Isn't it like the same thing, but only from 0 up because you have the radical and
Right. So now here's a function where I've mixed two different kinds of functions. There's a rational function mixed with a radical function. So now what you do is just like you look at individual pieces and you sort of figure out what restrictions you need for each piece. So now you realize that for radical x, we need what to happen? X must be greater than or equal to 0, right? For x squared minus 9, we need x squared minus 9 not equal to 0. So there are two things I have to fulfill here. So I already know where this guy, what's bad for this guy, right? So I know x cannot be minus 3 or 3. And I know that x can just be greater than 0. Now if I were to graph this again on the number line, you just graph one at a time, right? So let's look at the minus 3 to 3 guy, right? And I know that this will work anywhere for one of these functions. Then I look at the other guy, greater than or equal to 0, right? So 0 is in between these, I can be equal to it. And so the other function would work here, and then everywhere there. And basically what you look at now is just the overlap of the two, right? What region do I choose to fulfill both restrictions at the same time? Well, clearly over here, there's only one function that's satisfied. And over here, we have both being satisfied except at this point, right? So my overlap happens here, from 0 to 3, but I have to avoid 3, and then they both work over here. Right? So pictorially, I can say here now that the domain of J is what? 0 to 3, like that? Is that correct?
No.
Would 0 be included?
0 is included, right? I could be equal to 0 here, and definitely 0 can be shaded in according to both functions. So you put that bracket, right? So you put a bracket when the number can be included, you leave an open parenthesis when the number cannot be included. Let's go back over here. E. So what's the domain of R? What do we need? Right, well it's an even radical, right? So we need that x squared, x plus 3 must be greater than or equal to 0, but also x plus 3 cannot be equal to 0, right, because it's in the denominator, which means ultimately what we need is just x plus 3 is strictly greater than 0, right? Which would mean x is greater than 3, strictly speaking, which means minus 3. So it means minus 3 have to be bigger than that, strictly bigger, which means the domain of R is what's the domain of R? Negative 3 to infinity, like that, right?
No.
Right, 3 is not included. Because if I plugged in a negative 3, I'd actually get 0 in the denominator, which is very, very, very bad. So those are domains. Any questions on any of that? This again should be a review for most of you, hopefully. Hopefully I didn't say anything totally crazy here. Moving on. Well, this is kind of an important topic. I don't know how much we're going to utilize this in Tool 5, but just to be on the safe side, let's talk about it. Symmetry. Even and odd functions. Definition. F of x is said to be even if f of x, f of minus x equals f of x. Meaning, if I replace every x in that function with a negative x, it made no difference. This is called an even function. Example, f of x equals x squared is an even function. If I replace x with negative x, it's not going to make a difference. The square is going to kill the negative. F of x equals 2 minus x to the 4th is also an even function. If I replace x with negative x, it's not going to make a difference. Why do we like even functions? There are many applications that they're easier to work with. In particular, even functions are symmetric about the y-axis. So for example, if I look at y equals x squared, you will notice that's a mirror image. The right side of the y-axis is just a mirror image of the left side. It's you have symmetry on both sides. A lot of times later on when we're even doing calculus, we're going to be computing things based on functions, and we're going to realize, well, the right side is kind of the same as the left side, so because we know it's an even function, we can do half the work, right? Just figure out what's going on the right side, and we'll just double it to figure out the left side, right? That's sort of where knowing that something is even is going to come in handy, right? It'll cut down on the amount of work you have to do sometimes. So that's an even function. So you can tell when something is even by, if you know the picture, you can just look at the picture and say, oh, it's exactly the same on both sides. Or by the formula, all you have to do is just replace x with minus x, and if it doesn't make any difference, it's even. A function is called odd if f of minus x is equal to the negative of f of x. Another famous example of an even function is the cosine function, but we don't really do trig in this class, so we won't have to know. But yeah, a function is called odd when, if you replace all x's with a negative, you get the negative of the original function. Example, f of x equals x is an odd function. F of x equals x cubed is an odd function. Right? And basically all powers of x where the power is odd ends up being an odd function. Right? So if I replace x with negative x, I get the negative of the original. Right? If I replace x with negative x, I get the negative of the original. Odd functions are symmetric about the origin. Now that term can kind of be, that phrase can kind of be confusing, so let me describe what it means to you to be symmetric about the origin. So for example, y equals x. Here's the graph of y equals x. Here's the graph of y equals x cubed. Symmetric about the origin means if you take the right side, you flip it in the y, and then you take that and flip it in the x, you get the other side. Right? Same thing here. If I take this and I flipped it in the y, I would get something that looks like this. And then if I take that and flip it in the x, I get this side. Right? It's called being symmetric about the origin. It's kind of like you take this and you tilted it around, rotated it around the origin. Right? Whenever a function does that, it's called an odd function. And there are going to be times when, similarly, if we're looking at something between a function and another line, you can see that for an odd function, the right side will actually be like give you the negative value of the left side. So again, that will cut down a lot of work for us. We know that ultimately these both sides will cancel each other if we're giving them values. So we don't have to do anything. So that's symmetry. Of course, functions can be neither. So you can have a function, it can be odd, it can be even, or it can be neither of these. So you should know that. For example, f of x equals 1 plus x cubed is neither even nor odd. Right? Why? Well, what happens if I take f of negative x? Well, that just means I get 1 plus negative x cubed. Well, that just means I get 1 minus x cubed. Right? Now, this is not the same as the original function, nor let me write that over here. Neither even nor odd, y since if I take f of minus x, I would get 1 plus minus x cubed, which is going to be 1 minus x cubed. Now that is not the same as the original function f of x, right? Because it will be 1 plus x cubed. Nor is it the negative of f of x, right? Because the negative of f of x would be what? Minus 1 minus x cubed, right? So if I take the negative of this, I get minus 1 minus x cubed, which is, again, not that. So I neither have the negative nor the original function. So this function is neither even nor odd. It does not exhibit either of the symmetries that I just mentioned. In fact, if I were to look at 1 plus x cubed, what would it look like?
I guess it would start at 1 on the y-axis,
Yeah.
and it will follow that same curve that as the x cubed, just starts at 1, not the
Yeah,
order.
just shift it up, right? This is y equals 1 plus x cubed. Now you'll notice if I take the mirror image of this guy over here, I should get this, but that's not what I got. And if I flip this over here, I would get a curve down here, which is not that, right? It doesn't have that symmetry, either. Right, so it's neither symmetric about the origin nor the y-axis, so it's neither even nor odd. And I can tell that by looking at the graph, or by just examining the formula by replacing x with minus x. Just something to know, we're not going to take advantage of this piece of knowledge right away. It's really come in handy during the second part of the course, but for now, just know that it's out there, know that it's possible. Another very important idea that we are going to take advantage of pretty soon, actually, is whether knowing a function is increasing or decreasing. Definition. A function f of x is increasing on an interval if f of x2 is bigger than f of x1 when x2 is bigger than x1, i.e., it's not sound so mathy, the graph goes up as you move from left to right. Right? That's called an increasing function, or you can say it's increasing on a certain interval. So, example, y equals x is an increasing function. Right? As I move from left to right, the graph keeps getting higher. Right? That's an increasing function. That is an increasing function, right? You're going up as you move from left to right.
Anything with a positive slope is an increasing function.
Yes. A better way to say that is anything where the derivative is positive on the interval, we say it's an increasing function on that interval. But we'll get to that. A function is decreasing when the opposite happens. If f of x2 is actually less than f of x1 when x2 is greater than x1, i.e., the graph goes down as you move from the left to right. examples. Y equals minus x, or minus x plus a little bit. That's decreasing. That's decreasing. That's decreasing. That's decreasing. Right? As you move from left to right, you're getting lower and lower and lower. That's called a decreasing function. Note, a function may do both or neither. So you can have a function that exhibits both behaviors, maybe repeated over and over, as in the case of sine and cosine, which we already have to know about. So for example, y equals x squared is such a function. It's not always increasing, it's not always decreasing either. It's just doing one at a particular time. Right? So notice that on this side of 0, you keep dropping as you move from left to right. While on that side of 0, you keep getting higher as you move from left to right. So over here, we're decreasing, while over here, we're increasing. Right? So here's a single function that does both. For example, y equals x cubed is another. Let's make it more interesting. Let's say x times x minus 1 times x plus 1 is going to be a cubic function. That guy is going to look like this. Now, what if I ask you find? Now, if you tell me where something is increasing and decreasing, we say you found the interval of increase or the interval of decrease. So let me say that. Find the intervals of increasing and decreasing for y. In which case, you can shorthand this with I and C. And I want you to tell me what intervals is this increasing or decreasing?
For the cubic function?
For this function that I just mentioned.
Yeah.
Yeah. How would you say that? Yeah?
It's increasing from -1 to negative, I'd say like a half.
Could be like a half. Okay, so at this point, which is another reason where calculus is going to come in, we don't really know what this number is. So let me just call it a number like minus a, and call this down here plus positive a, right? Because it's going to be symmetric. So how would you state it? Increasing where?
So -1 to negative a. Or like
No.
negative infinity.
Negative infinity
Yeah, negative.
to minus a, right? Because it's going from here, it's coming up the whole time, okay?
And from a to
Right. So in this region, we're increasing because we're going up as we move from left to right. And over here, we're increasing because we're going up as we're moving from left to right. So I can just attach those two with a union. Right? Where is it decreasing?
From negative a to a.
Between these two numbers here, I'm going down as I move from left to right. From negative a to a. Right? Notice that I sort of didn't include a in either one, because if I'm at a, technically I'm not moving up or down. I'm sort of leveled, I'm sort of flat. Right? Now what do you notice about these 2 points here?
The minimum and maximum.
It's like a minimum and a maximum, at least locally speaking, right? Like in this region, if I zoom in, this is going to be the highest point. In this region, if I zoom in, this is going to be the lowest point. Now remember that example we did yesterday where I was talking about, how to make the most money from my hot dog stand. The important point that I wanted to be able to access was the maximum point, right? I wanted to maximize my profit, right? So you see things like these, maximums and minimums, those are really important for us to be able to find, right? And here's a great way to describe a maximum. How can you describe in terms of increasing and decreasing? What happens to get a maximum?
The increase must stop and the decrease must begin.
Yeah, you have to be increasing on the left, decreasing on the right? So if I know a function that is continuous, it keeps moving, but I know at some point it's increasing and then it switches to decreasing, I must have hit a maximum somewhere there, right? Vice versa. If something is decreasing on the left, but increasing on the right, and the function is still going continuous, there's no holes or anything crazy happening, I know I must have hit a minimum at that point. Finding maximums and minimums are going to be very important, and hence, finding where something is increasing or decreasing is going to be very important. Now here for this function, you can look from the graph, and it's okay. But what if I gave you a really nasty function that you didn't even know what the graph looks like, right? How do we figure these out? These are the kinds of problems that we're going to tackle, and that's why calculus is going to be useful for us. Identifying maximums and minimums is a super important idea. In order to identify those, we're going to need to be able to identify increasing or decreasing in much more complicated functions than this. So that's why I'm going over all this, because I want you to kind of see the point of why we're doing these things. What else? That's actually it for 1.1. We've completed section 1.1, everything I wanted to tell you from 1.1, which means the homework for 1.1 is due tomorrow. And let's move on to 1.2. I think this is a short section. Well, relatively speaking, 1.1 we did a lot. 1.2 is going to be a little bit shorter. There's one main idea we want from 1.2. Our syllabus kind of said to skip the other one, but I'm kind of going to just talk about it a little bit anyway. I think it'll be beneficial. So this is talking about combining and transforming functions. Were there any questions left on what we did from 1.1? Anyone totally unfamiliar about any of this? Well, 1.2 shouldn't be unfamiliar either, but of course, if you have questions, ask me. Well, technically nothing in, well, maybe exponentials might be new to some of you. But so far, like up to 1.3, we shouldn't really be seeing anything new. It's all kind of review. I know you guys are bored, but we'll get to the exciting stuff pretty soon. Combining and transforming functions. Let's talk about two main ideas here. One, I want to talk about the composition of functions. Composition is a technical term, I'll describe what that means, and the transformation of functions. Less important idea. It's kind of important, but I'm not going to emphasize it here. Basically, operations on functions, which means adding two functions, subtracting one function from another, multiplying one function by another. But it's very intuitive, so I don't really need to talk about it at length. So let's talk about composition of functions. AKA function composition. composing functions. Etc. Technically, when you say combining functions, you could be either talking about 1 or 3. So I won't say combining. What's the idea behind the composition of functions? What am I talking about when I say I composed one function with another?
You mush them together.
What does that mean? I did this with the functions.
No, like here's one function, here's another one, you just squish them together.
That sounds like multiplication.
No,
That would be a better description of multiplication.
Is it like a piecewise one kind of thing?
No, not really. When I talk about function, I'm talking about things like f of g. Remember that guy?
Yeah.
What did we do with that guy?
You put G into F.
Hmm?
You put G into F.
You put g into f. You basically it's plug one function into another. Right? So this is like the idea if you're taking an entire function as the input to another function. When you actually do that, you say you've composed the functions. You've created a function composition. Notation for functions. F and G. F circle G of X is called F composed with G. F of G is another way you might call it, kind of like f of x when you say f of G. And it is defined basically how you're going to think of it as f of G of X basically means f of. You actually replace the X in the F with the G, f of G. It is the function obtained when G is plugged into F. Right? So you take the guy on the right, you plug into the guy on the left, and you say that you've composed the functions, or you're taking a function composition. We've actually done this before with the difference quotient, right? When I told you f of x plus h, I was actually taking a function composition. Example, let's say my f of x is x squared plus 1, and my g of x is 2x plus 3. Find f of g, g of f, f of f, g of g, f of g of f. Okay. F of g, you can write it of x if you want. What would f of g look like? Well, this means you take f of g, right? Now, what do we do? Remember what we said when we put something in brackets? What do you do?
Replace anything.
Everywhere you see an x, you're going to replace it with what's in the bracket, right? So let's do that. Here I have x squared plus 1. Now instead of x, I want g. So I'm going to open parentheses. And what's something squared plus 1? What is the something? G. Okay? But what is g? G is this guy. That's 2x plus 3 squared plus 1. That is f of g. Wasn't enough? Yeah?
4x squared plus.
Sure, you can multiply this out. If you want 4x squared plus 6x plus 9 plus 1, that would be 4x squared plus 6x plus 10. You won't always need to do this. It depends on if you're asked to do it or if there's another convenient reason why.
That's all my tests and stuff, because they give you extra for that.
If I just ask you to find this, then I don't care what you do. You could stop here. You know, it would depend on the problem. Like if I ask you, find f of g in the vertex, then I leave it here, because you can talk about the vertex right away. It's a lot simpler. Yeah, what about g of f? Well, this just means you take g and you plug f into g. But what is g? G says 2 times blah plus 3. What is the blah? Whatever I put in the bracket is the blah. Right? So that's going to be x squared plus 1. Right? Let me write it out here. Basically, I'm going to put f of x to replace where my x was. But I know that my f of x is actually defined to be x squared plus 1.
How do we get 6x if it was
2 times 3 times 2. That should be 12x. Someone's paying attention. This again, you might leave it, but you can also multiply out. This is 2x squared plus 5. F of f. So this basically means I take f of x. My f, the rule for f was to take something, you square it, and then you add 1. What is the thing I want to take and square? Well, f of x itself. And f of x is to take x squared plus 1. And you can leave it like that, or you can multiply out x to the 4th plus 2x squared plus 1 plus 1. Next I have g of g. Which means I take g and I plug it into g. Which is basically, I know it's g was 2 blah plus 3. This time my blah is g, which means it's 2 times squared plus 3 plus 3. Okay. And the last one was f of g of f. What does that mean? It's f of g of f. Now a couple ways you can do this. You can break it down into pieces. You can first find g of f, and then you plug that into f again. Right? So I know that g of f, we actually found that before. That was what? Well, it was 2 times x squared plus 1 plus 3. Right? Which was 4x squared plus 2 and 3. Right? That was my g of f. This means that f of g of f is just f of 4x squared plus 5. This means in my function that tells me to square and add 1, I'm going to plug in the expression 4x squared plus 5. And that would be your answer. You just plug in twice. Or you can keep going. You want to take the right guy, plug into the left guy, plug into the left guy, plug into the left guy. You can do it over and over. Any questions so far? to talk about domains, let's talk about what's happening. Composition of functions simplify our lives. Basically how you want to think of them is that they cut out the middleman. So let's say here you have the domain for f. Or domain for g. Here you have the codomain for g. Which might also be equal to the domain for f. And here you have the codomain for f. Basically how you want to think of it is that g takes a guy from here and moves it over there. G does that. And then f takes people from here and moves them over here. Right? Basically what f of g does is it starts here and it just jumps all the way to here. That is what f of g would do. Right? So first g is going to do something and it's going to give you an answer. You plug that answer into f and then f is going to give you another answer. The composition just jumps over the middleman, right? It simplifies your process, right? It makes one big function that combines several other functions, right? And of course, in theory, the domains and the codomains will match up and sort of nicely. The domains. The domain of f of g is the intersection of the domains f g and the example. Let's say f(x) equals square root of x. This is equal to 1 over cube root x squared plus 1. And then I said, find the domain of f of g. Where does that function work? Well, first, what is f of g? F of g would be what? It's f of g, which means it's going to be 1 over cube root of, yeah, I'm going to put in g here, I'm going to square it and add 1. In other words, it's the cube root of radical x squared plus 1, which is cube root of x plus 1. Now, what is the domain of that function? Huh? So for f of g, we need, remember the cube roots can work for positives or negatives, right? So I don't even care. about positive or negative. The only thing is I don't want it to be 0 because it's in the denominator. So I need that x plus 1 cannot be 0, which means that x cannot be minus 1. Right?
So happy.
I don't know why she's so happy to see me. Oh, she actually did well. She's in my 209 class last semester. So here, notice that for this function, anything but minus 1 can work. So anything over here, and anything over here. However, you have to kind of remember that this was actually a function composition, right? This wasn't the function as it was given. I first started with this function. Now for this function, what did we need?
Anything above 0.
X had to be bigger than 0. So while this worked for f of g, for g itself, g had to be here. So you know what? It's not right for me to take this as a domain, because remember what's happening with function composition. First g is applied, then f is applied, right? Now if I can't even plug in negative numbers over here, there's no way they would work in here, right? So it turns out that the domain, in this case, the domain of f of g is actually going to be only things that are 0 or bigger, right? Now this function on its own can work for anything that's not negative 1, but it's not that function. It was actually a radical plugged into that function. And in here, I couldn't plug in any negatives, right? So I have to examine both functions separately. I have to examine the guy that was plugged in, and then examine the result. And I need the overlap of both of them in order to work. So sure, this will work in this function, but it's not going to work in the radical. And I need it to work in the radical, because I couldn't plug it in the first place.
But isn't the domain of f of x just by itself literally anything, since even the negative number
Yeah,
will,
the
cancel?
domain of f is everything will work. That is correct. But g messes up, and the result of f of g messes up. You need to make sure that both of them will work when you're plugging one into the other. So that's compositions and the domains. Again, still in review territory, but if ever anything's unfamiliar, just stop me and you need to ask a question. We will move on. Transformations. Basically, this is talking about shifts, stretches, shrinking, that sort of stuff. Some common ones. Given f of x. Right, so let's say I'm given a function. I can quote unquote transform that function using several mathematical operations. And doing it algebraically will do something to the graph. So for example, if I take f of x plus c, and my c is greater than 0, what does this do?
Increases the value of f of x.
What does it do to the graph? How can you describe it?
Should.
It's a shift where?
Wait.
Oh,
Oh. Right? F minus c, my c is greater than 0, that's a shift down. Right? Once you're adding outside, right, what you're doing, remember f of x is like your y values. You're adding a number to all your y values. So everything on the y-axis is shifting up, right? Or shifting down. There's a difference when I add something to each x value, right? Now, if I put a positive number here, what's it going to do? It's actually going to move left, right? When you're changing the x, it's sort of counterintuitive, and you have minus c. This actually shifts right. f of, if I multiply c by x, my c is greater than 1. Or if I divide x by c, where c is greater than 1. Okay, what does multiplying by a number bigger than 1 do?
Doubles it.
Remember, for x it's actually counterintuitive. This actually shrinks. This one will stretch. Stretch, let me be specific, shrinks horizontally. Shrinks, stretches horizontally. I can multiply on the outside though, c times f of x, or I can take 1 over c times f of x. And here, let's see b greater than 1. B greater than 1. This now stretches vertically. This one will shrink vertically. And just to do a couple examples, just to see, do some examples on y equals x squared. Right? Basically, I know that y equals x squared looks like this. Right? But based on transformations, if someone asks you to draw y equals x minus 1 squared, you shouldn't have to figure that out or plot points and infinity. No, you just realize that the x was changed to x minus 1. That's like an x minus c, which means the only thing that's going to happen is just a shift to the right by c units. This shifts by c units. So in other words, the graph of this one is just going to be the graph of that one, shifted to the right by 1 unit. Right? Similarly, if I had y is equal to x plus 1 squared, this just means the graph was shifted to the left by 1 unit. All right, so knowing about transformations, it allows me to shift graphs. If I had multiplied here by a 5 or something, it actually stretches this way. You probably wouldn't notice it. Because it's going to infinity anyway. But these are some examples. Other important kinds of shifts are reflections. Transformations are reflections. If you take minus f of x, this reflects in the x-axis. If you take f of minus x, this reflects in the y-axis. Example, let's say I have y equals x squared. I know that that's that guy. If I look at y equals minus x squared, what I actually do is I reflect in the x-axis. I turn everything upside down. If I have y equals x cubed, that's this guy. I get rid of this. I'm just doing a lot of pictures. Or if I have y equals minus x cubed, if I write it that way, what do you think of it as is being flipped in the y? So it's going to look like this. Although x cubed is not such a great example because you actually look the same if you flipped here. Or if if I have some function here, f of x, then if I take f of minus x, it's going to look like this. So again, pictures are very important to us, graphs, but you don't want to have to redo all your calculations if someone tweaks your graph, right? So you should just know how to quickly figure out what's going on. Yes.
What happens when? So what happens when it's f of c times x? Again.
Oh, that causes a shrink if your c is bigger than that.
Shrink vertically, horizontally.
Let's get rid of here. F of c times x.
Yeah.
So for example,
Assuming.
let's say here I have f of x and it looks like this. And then I take f of 5x, right? Like I multiply the x by a number. It's actually going to it's affecting the x, so it affects horizontally. It's going to shrink it this way. It's actually going to squish it by 5
So it's
times.
kind of like zooming out on something.
Yeah, so you squish it. Right?
And
if I did 1/5, if I did f of 1/5 times x, it will actually stretch it out. It will be like. Right. So when you're affecting the x, it's sort of counterintuitive. Multiply by a bigger number actually squishes you, and multiply by a number less than 1 actually stretches you out. The idea of why that works is because you have to think of how your inputs have to compensate for the change. If I made this 1/5 less, to get the same y value, my x has to be 5 times bigger, right? So to get that same y value, my x has now be 5 times bigger, so it takes me 5 times as long on the horizontal to get back the same y value. Right. Similarly here, if I multiply by 5, now to get the same y value, my x has to be 1/5 less. So if before I needed to get a 1, y value of 1 when my x was 1, now that y value of 1 has to occur when x is 1/5. So everything's going to shrink this way. So it's kind of, with the x, it's like your input has to compensate for the change. You're not just moving y values around, which is kind of different.
No, Professor.
Yeah.
All those properties of whether a function is increasing, decreasing, even odd. When you tweak the functions in such a fashion, like f of x plus c minus c, f of x plus c and then minus c inside multiply, that still retains all the properties of said functions.
No, not necessarily. No. Which, after we talk about derivatives, we'll get to that, right? One way we're going to determine when functions are increasing or decreasing is using the derivative. And in the case of transformations, we're going to use a derivative technique called the chain rule. That will tell us how the function is going to be changed. What else did I want to tell you? That was almost it. But I just want to mention this. I don't know how much it's going to help. But they talk about decomposing functions. Basic idea here is given an f of g, could you figure out who is the f and who is the g? Example, if I told you here's a function decompose into f and g. I don't necessarily like this idea because you could kind of technically, there are an infinite number of answers you could choose, but they kind of want you to go after the most intuitive one. What would be the most intuitive answer? So you want to look at this as one function being plugged into another one. How do we look at that? Yeah.
I think maybe like a ax is like 2x X cubed plus 1.
Yeah, so this, it kind of intuitively, you feel like this is really kind of excessive. I mean, it should be like an x cube. We have this whole mess cubed, right? So I can look at this guy here as like an inside function, like something was plugged in, right? So I can look at my f as x cubed plus 1 and my g as that 2x squared plus 3. And if I take this and plug it into that, I get this. So it's kind of going to be the obvious intuitive answer that you can quickly see. I suppose why they talked about this in this chapter is because when we do get to the chain rule, you're going to have to be able to identify the inside function and the outside function, right? Which in this case, your f would be the outside function, your g would be the inside function. And we're going to use that to our advantage to figure something out. Three, just to mention it, combining functions. All right, this just means given f of x and g of x, consider the functions. There's f plus g of x, which basically just means you add the two functions f and g. Or f minus g of x, you can subtract one function from another. We're going to be using this idea a lot. You can multiply one function by another. It's called, in shorthand, it's just fg of x, which just basically means f of x times g of x. And we have f over g of x. Just means f of x divided by g of x, which will work as long as your g of x is non-zero. Yeah, so there's nothing really to talk about here. Just take two functions, you add them together, multiply them, divide them. And that's 1.2. So homework for that is due tomorrow as well. Now we're going to finish 1.3, so we have 3 homeworks. Two more examples. I don't, as professor, I suddenly don't understand. I have a question.
Can you go to that whole section?
Can you go over the whole section? I'll start 1.3. We won't finish it, but it's totally familiar stuff. It's basically straight lines. I'm going to remind you of the equation of a straight line and the slope of a straight line and all that stuff. But I still won't finish it because I'm going to want to do some word problems here, which we won't have time for. Linear models. And I believe it's called rates of change. So we call a linear function is one. Y equals mx plus b. Right? Its graph is a straight line. And of course it's non-vertical. There's a concept of a vertical line, but a vertical line is not a function because it doesn't pass the vertical line test. So technically it's not a linear function. FYI. A vertical line has the form x equals c, where c is a constant. It is not a function. So this is just like a line that's a vertical line that passes through x equals c. So now let's talk about these guys. y equals mx plus b. Very important formula to remember. This is called, what's the name for this? Anyone remember? It's called the slope-intercept form for the equation of a line. And in this case, m is the slope, b is the so-called y-intercept. That's why I call the slope-intercept form, because those are the two numbers that you see. And the y-intercept is where we touch the y-axis. Slope is and we're going to reinterpret this into a rate of change, but it's a measure of the steepness of the line. Slope basically equals rise over run, and if we know 2 points, the line passes through, call it x1, y1, and x2, y2. Then the slope m is equal to, what is it? y2 minus y1 over x2 minus x1. Okay. So the idea is, boom, here we have a straight line doing its thing. If I know 2 points where here's one x value, the corresponding value of y1. Here's another x value. The corresponding value is y2, and I know the coordinates of these 2 points. Then what I can do is I can form a little triangle here where this is the rise, right? Which is just a vertical distance. I want to find the vertical distance. I take the top minus bottom. And so this is equal to y2 minus y1. And then this would be the run, right? So how far you move horizontally. That's going to be right minus left. That's how you find the vertical distance, x2 minus x1. So if you take rise over run, you get y2 minus y1 over x2 minus x1. It's kind of a measure how steep, right? Clearly the bigger this number is, if in the same run you have a larger rise, it means you're steeper, right? We can write the following. M is equal to, let's say my x2, y2, I wanted to call just x comma y, right? The generic point this line passes through. Then this would become y minus y1 over x minus x1, which means I can write y minus y1 equals m x minus x1. This is another form for the equation of a line. This is called the point slope form. Right? Because I know a point on the line, which is x1, y1, and the slope. And by the way, here where this line passes through the y-axis, that guy is your b from the previous form. So that's called a point slope form. So intercept is of course useful if you know obviously the slope and the intercept. And point slope form this is easier to use if you know a point which may or may not be the y-intercept. The line passes through. And its slope. Maybe next time I'll do a quick summary of this to show you how I'd like you to remember it. There's an interesting interpretation of slope you may or may not have thought of or have seen. It's going 80 miles an hour. Did you guys see that YouTube video? Did you see it? Never mind. And we graph its distance covered versus time. The guy was asking his girlfriend, if we're going at 80 miles an hour, in 1 hour, how far would we have traveled?
Oh,
Right? And she's like, took like forever to figure it out. And her reasoning was like, okay. Anyway, yeah, so let's say we were plotting distance versus time, right? So I'm putting an interpretation on my x value and my y value. Now my time is the independent variable, right? So, and I start the clock somewhere, let's say the distance is 0 away from me and no time has passed. However, I know after 1 hour, the distance is now 80, right? Now, I'm not sure what the car did in between, but overall, this is like a general, overall like a general idea of what the car was doing. Now, if I were to measure the slope of this line, how could we interpret the slope of this line? Yeah. Speed. In fact, I can interpret this as the average speed. Well, to be technically, I'm talking about its velocity, but whatever. Right? If I take rise over run, my rise is going to be 80 miles minus 0 miles, right? Over 1 hour minus 0 hours. Well, that would give me 80 miles per hour, right? My slope here kind of was the speed. I can kind of look at the slope of a straight line in some sense as how fast this thing is moving, right? Now that is an idea that we're going to take advantage of. when we get to chapter 2, really. We're going to talk about the rates of change of something, how fast something is moving, how fast is it increasing or decreasing. It's going to come down to figuring out how to measure the slope. So 1.3 is not done. I have more to talk about here, but 1.1 and 1.2 we finished. The homework for that is due tomorrow. Make sure you get it done, and we'll answer questions. All right, see you tomorrow. Done.